First of all, let me thank you all for being here today. My name is Victor Gomez, and I am the presenting author of the communication titled Evolution Algebras, whose evolution operator is homomorphisms, by Professors Fernández Ternero, Nuñez Valdes, and myself from the University of Seville in Spain. This presentation is structured as follows. We start with the main objectives of our research, to later give an overview of the concept of evolution algebras and some basic definitions about them. Next, we will focus on the case in which a certain operator, called the evolution operator, is homomorphism of algebras. And finally, we will see some open problems about these algebras. The main purpose of our research is to obtain a classification of a family of evolution algebras, those in which a certain operator, called the evolution operator, is a homomorphism of algebras. For this, we have studied the problem depending on the rank of this operator. In previous works from ourselves, we have characterized the cases with ranks 1, n-1, and n, which allows to obtain the complete classification for dimension 3. And the objective of this paper is to obtain a characterization for rank n-2 that allows to classify these algebras up to dimension 4. We first define an algebra as a vector space endowed with a linear product, and we will say that this algebra is an evolution algebra if there exists a basis such that if you multiply two different elements of this basis, the result is 0. We will call this basis a natural basis, and the product of an element with itself can be written as a linear combination of the elements of the basis. If we group these constants in a matrix, we form the so-called structure matrix and observe that columns J of matrix A give the products of E sub J with itself. Besides that, we have to remark that evolution algebras are commutative, but they are not associative. For example, if we consider this algebra with the square of E sub 1 and E sub 2 equals to E sub 2, and we make this product, if we associate in this way, we obtain E sub 2, but if we associate it this other way, we obtain 0. Next, we give the definition of non-degenerate and degenerate evolution algebras. An evolution algebra is said to be non-degenerate if the squares of the elements of the basis is non-null. If there exists an element of the basis with null square, it is said to be degenerate, and these concepts are equivalent to the existence of null columns in the structure matrix, so that the first matrix corresponds to a non-degenerate evolution algebra and the second one corresponds to a degenerate evolution algebra. To end this introduction, we define the evolution operator as the endomorphism which maps each generator into its square. Notice that by this definition, the matrix representation of the evolution operator is the structure matrix A, because the columns of matrix A are exactly the squares of the elements of the basis. We'll now proceed to study when this operator is a homomorphism. We say that an endomorphism is a homomorphism of algebras if it satisfies this equality. And in the case of the evolution operator, this is equivalent to these two identities, where C sub j is the column J of the matrix A, and this sign denotes the Hadamard products, that is the element by element multiplication. And we want to obtain all the structure matrices satisfying this condition up to reordering of the basis elements. And now we distinguish two cases. The first one is when the algebra is non-degenerate, and in this case we do the study depending on the rank of of the structure matrix. For example, for maximum rank, the fact that the evolution operator is homomorphic is equivalent to the structure matrix being a permutation of the identity matrix. For rank n-1, it is homomorphic if and only if we can rearrange the bases such that the structure matrix is of this form, where A sub 1 is this matrix and A sub 2 has its two rows equal, O is the zero matrix, and P is a permutation of the identity matrix. Finally, for rank 1, it is equivalent to the lambda vector being orthogonal to the first column and its square, where each lambda is the constant by which the first column must be multiplied to obtain the corresponding column. Next, we give a characterization theorem for rank n-2. In this case, the evolution operator is homomorphic if and only if we can rearrange the bases such that the structure matrix is of this form, with the matrices O and P the same as before, the zero matrix and a permutation of the identity, and the matrix A sub 1 and A sub 2 match one of these descriptions. K gives the dimension of the third matrix, and this matrix can be given explicitly. For the second matrix, in the first case, the three rows has to be equals. In the second case, the first two rows are equals, and the third one is null, or a basis vector, that is, has an only entry equal to 1. In the third case, the columns are of this form, a constant plus the first column multiplied by another constant, and the vector formed by the first constant is 0 or a basis vector. In the last case, the first two rows are equal and the last two rows the same. Next, we are going to review the main ideas of the proof. Since it is quite a long demonstration, and for more details you can see the complete proof in the full paper. The first step is to define this set, which is the one formed by those coordinates such that there exists a vector in the null space of the matrix A with this coordinate distinct to 0. The next step is to prove that if I is in this set, then the column I belongs to the null space of the matrix. With this, we later deduce that the cardinality of this set has to be 3 or 4. And next, we rearrange the element of the basis so that this set is the 1, 2, 3 or the 1, 2, 3, 4. Later, we check that with this rearrangement, the structure matrix is of this form, with O the zero matrix and P a permutation of the identity matrix. And the last step is to deduce all the possible structures of matrices A sub 1 and A sub 2. On the other hand, when the algebra is degenerate, we can get all possible forms of the structure matrix in a given dimension n. By the following algorithm, in step 1, we obtain all matrices A prime of one dimension less, and in step 2, for each A prime, we find the vector space orthogonal to this one, and then the searched matrices are these ones with B in this orthogonal space. We have implemented and run this algorithm for multiple dimensions. In this graph, we have represented the time it took to execute according to the dimension of the matrix. We have split the experimental data in two parts, training and test, the blue one and the red one, and we have calculated the least square cubic polynomial fit to our training data, and that is the black curve. And as you can see, the experimental data fit this model, so the algorithm has cubic time complexity. In these tables, you can see the experimental data in the first table, and in the second one, the comparison between the test data and the expected time by the cubic fit in higher dimensions. Uh, and in the last column, you can see the relative error between the two values, which is very small. To finish, we see some open problems on that subject. The first one is to study when the evolution operator is a homomorphism of algebras with rank between 2 and n-3. The second one is to transfer the results obtained to other branches of mathematics that have direct connection with evolution algebras. For example, each evolution algebra has associated a directed graph such that the edge starting from e sub I to e sub j has weight a sub ij. And starting from this, how is the fact that the evolution operator is an endomorphism of algebras expressing the graph, and what properties can these graphs have? We end this communication with the bibliography used. The first article is the one in which we begin to study the problem of when the evolution operator is a homomorphism, and the last two references are those in which evolution algebras were firstly introduced by Tian. And that's all. And thank you so much for your time.